presentation. So I'm Céline Coutrix, and this is Jennifer Pearson. And we choose to present together because this was a very nice and balanced collaboration between our two universities, so Grenoble in France and Swansea in the UK. So the work started by seeing that often mobile interaction lacks tangibility. So I'm going to show 3 examples of this. For example, if you pilot a drone with your tablet, what you want to look at is the drone that you're piloting. If you are a sound engineer and you're doing a balance for a performance, well, who you want to look at is the performer on the stage in order to communicate with this person. And for example, if you're crossing the street while using your mobile phone, what you should look at is actually the bus that is on the street. But what happens very often is that we need to look at our mobile graphical interfaces because otherwise we don't have much feedback except the visual one. So this often results in low preference, low performance, but sometimes also low safety. So our concept idea to cope with that was the introduction of emergeables, that is from the graphical widget having a tangible widget that emerge from the screen for the user to use it. So I will show you a scenario of use of this concept. So here is Alice, and she's watching a very important soccer game. So she does not want to miss a second, so she has all her eyes on the TV. And at some point she wants to lower the light for better comfort, so she takes out her mobile phone and she points at the light. And then a tangible slider morphs out from the surface, and then she can actually acquire the slider and manipulate the slider without looking at the interface. And then this tangible slider can morph back into the surface. Then during halftime and advertisements, she leaves the living room and she goes to the kitchen to wash the dishes. Here, and so at some point someone rings at the door, and so she wants to lower the volume, but just the right amount to hear the person at the door, but still know if the soccer game is beginning again. So a tangible dial emerges from the surface so that she can use it while walking and paying attention to what's on the floor or down the steps until she reaches the door. And then the tangible dial can morph back into the surface when not in use. So this allows to operate mobile devices while being eyes-free, but we envision several benefits for this idea. First is that compared to new interaction techniques, what we saw is that here we have the known tangible controls that we have everywhere. So the user doesn't have to learn a new interaction technique to use this. Another approach that was introduced before was also to add some tangible controls onto the tablet. So for this, compared to this, we provide the user with the opportunity not to perform this additional manipulation to add the sliders and the knobs on top of the tablet. And also, compared to previous work on buttons, what we wanted to provide the user is a continuous control for mobile interaction. For example, if you want to control the light, the sound, color, position, things like this. So in short, the benefits we envision for emergeables for eyes-free mobile tasks, it's the ability to use known tangible controls, that we have no additional configuration for the device, and also to provide for continuous controls. But the problem is that what you saw in the video is that this was a fake, so we don't have the technology yet to do this. So what we have today actually is that is very popular now in research, is those rod-like displays that people can touch and push. But it's still far away from the way we manipulate today the current tangible user interfaces. So our approach to explore this idea was to provide such a rod display on a mobile interface, but also to allow for further manipulations of the rods. So this is the new challenge that we wanted to address in the paper. Sorry. So the first thing we wanted to provide the user is the translation of the rod. So this should be animated and it's not. and also the ability to rotate the rods on the display. And an interesting axis that we wanted to explore is the resolution. What we have today is quite large rods on those displays. In the previous session, in this very same room, we saw a work where those rods were actually way smaller. So we can envision in the future that those rods will be so small that the user won't be able to see them or even feel them below their fingers. So then we have two questions. The first one is it worth the effort developing such a technology? Do we have a benefit for this? And how far are we today from the performance of such an ideal concept of an interface? So to answer these, there's two questions. We made a prototype. So the first one is a prototype that is simulating the high-resolution interface, and it was tailored for our experiments. So the idea is that we just rotated some panels and provided the user with, for example, here is a slider. And here is a second video where we see we have 4 positions predefined where we can provide either a flat surface, a slider, or a dial for the user. So this is simulating high resolution because the user manipulates real today's tangible controls. However, their shape and their location is predefined and tailored for the experiment. But it will allow us to start answering the question, is it worth the effort doing this in our experiment? And to answer the second question, like how far are we today from the performance of this kind of ideal interface, we made the second prototype that Jennifer will present now.
Thank you very much. So I'm going to explain to you now about our low resolution prototype. First off, I'll tell you about the design of it. It's actually a 4x7 grid of stencil rods, 15 millimeters in diameter. So each rod can move up and down independently and is mounted on a sensor that combines rotation and tilting detection. From this prototype, we can provide both dial and slider interactions. To create a dial, a single stencil is raised for the user to turn. And to create a slider, one stencil is raised. When the stencil is tilted, the next stencil along the line is then raised and the movement continues. So we tried quite a few different iterations of doing this before settling on this design. I won't bother you with the details here, but I can say that in our final prototype, each stencil consisted of a micro stepper motor, which we harvested from laptop CD drives, which facilitates the up and down movement of the rods, a navigation switch, which facilitates the rotation and side-to-side movements of each stencil, and some 3D printed components to form the top of each stencil and allow proper attachment to the electrical components. So when we put all of these bits together, it looks a little bit like this. That's the final rod. I painstakingly soldered 28 of these, put them together, and it looks a bit like this. So the final prototype contained 28 stencil rods and were controlled by 8 Arduino boards. So this meant that the prototype itself was quite large, but crucially it was still mobile, so users were able to hold it with one hand and control it with the other. This design allows us to emerge a dial or a slider in any location on the prototype surface, and the inspiration for this was from rod displays, as Céline described, and of course the pin pression toys that you may have seen on people's desks. So I'll just show you a quick demo video now, showing how the prototype works. So, is it playing? Yeah, so there's the slider interaction there, and the dial interaction, and once it's finished it can go back down into the surface. So it's important to remember that these controls can be positioned anywhere on the deformable surface. This video is showing a slider with 4 stencils, but it could be more or it could be fewer. And in this particular prototype, a slider of 7 stencils is the maximum because it's a 4x7 grid. So now I'll quickly move on to our experiment that we did to test this prototype. The point of this experiment was to evaluate the impact of resolution on performance with continuous mobile deformable controls. So it was a within subjects design with 3 interfaces. So the high resolution prototype that Céline described a moment ago, the low resolution prototype, which I just told you about, and a graphical comparison interface that was just shown here. You can see on the left there, that's a slider. On the rightmost is a dial. But the size, input resolution, location, and latency of each widget was the same across all three designs for the study. The sliders were 80 millimeters in length. They consisted of 4 sensors on the low resolution version, and the dials were all 15 millimeters in diameter, so that they were all comparable. Okay, so we also had 3 independent variables here. The resolution, which is the prototype, here. The complexity, which is either 1 widget or 2 widgets controlled simultaneously, or the widget itself, which is either a dial or a slider. So due to time constraints in this talk, I will only focus on the resolution and the widget parameters, but we did explore 2 widgets at once to acknowledge that people often do use 2 controls simultaneously for situations such as gaming. But like I said, I'm not going to discuss that here. So, of course, the order of the presentation of the resolution was counterbalanced on a Latin square design, and the order of the widgets was randomized to ensure a fair test. In all cases, the physical location of the widgets was also randomized to one of 4 positions. This was to try and avoid participants' reliance on motor spatial memory. And just a quick note as well, in the GUI case, only 1 operational widget is visible to the user at one time. For the others, the non-operational widgets retreated into the prototype surface to simulate them disappearing. So now for the setting of the experiment. The main part of the study involved users using the prototypes to control a graphical display projected on 2 separate screens. We designed the task so users would need to be looking at the screens, not the interfaces themselves. So users were asked to stand between these 2 projected screens and asked to perform a series of pursuit tasks that switched between the 2 screens every 15 seconds and lasted 120 seconds in total. The aim of this was to simulate performing a task while mobile, so participants were free to move around, move their entire body freely to face the appropriate screen. So I'll just show you a quick video of the pursuit tasks now. So if you look here, you'll see that the solid white line here is the user's controller, and the blue shaded areas are the target region. So we asked participants to stay within the blue target region at all times, and these target regions then moved at a constant speed and darted off at pseudo-random intervals every sort of 2 to 4 seconds. You can see here an example of the user controlling the white line to try and stay within the first target region. This one here is a slider. I think the dial has already been. And when the projected control switch screens, the participant was prompted by an on-screen instruction to turn around to the other screen to keep it mobile. So the measures we recorded here were accuracy, or pursuit accuracy, which tests the effect of resolution on performance via logs of participant tasks. The visual attention required to use each prototype. So we analyzed the video footage here, recording when participants looked down when controlling the widgets. And of course, the perceived usability. We got this via subjective ratings. We asked them to rate their ease of use of each system and also to rank each interface in order of how much visual attention they thought it required to use. So now for the results. When we compared performance, that's the pursuit error, we found that overall the high-res prototype performed better than the GUI, but results for the low-res versions were split between widget types. When we look at the effects of the type of widget on performance, the low-res prototype error rate for dials was very close to that of the high-res, which is useful, and both caused fewer errors than the GUI approach. We think this shows potential for the emergeable controls. When we look at sliders, the low-res slider resulted in more errors than the GUI, but the high-res slider performed better than the GUI, which suggests that the resolution of our sensor-based approach is close, but not yet sufficient to provide comparable accuracy to either high-res tangibles or touchscreens. Now turning to visual attention, overall, the high-res prototype required the least visual attention. This ranking was corroborated by the subjective rankings from participants who felt that the GUI required the most visual attention, followed by the low-res and then the high-res. When we look at dials, the GUI requires significantly more visual attention than the 2 emergeables, but there is very little difference between the low-res and high-res versions. In the case of sliders, the low-res slider requires more attention than the high-res, but lower than the GUI, which is promising for attention-critical tasks such as gaming or drone piloting. Subjective ratings also showed the value of the physical controls. So in conclusion, we have presented emergeable surfaces for eyes-free control of continuous widgets. We have shown the potential of the low-res stencil-based approach and shown the value and benefits of emergeable high-resolution tangible controls in terms of accuracy, visual attention, and user preference. Our future work in this area will start with how we can produce smaller, higher-resolution widgets and how best we can improve the slider interaction for stencil-based approach. Thank you very much.
Hiroshi from MIT Media Lab. I really appreciate, because you started from the vision, magical visions, then made up a video prototyping, then faced with the technical realities, like a Stone Age. I really agree. And making the pin is horrible, so much intensive work. We made 1,000 pins, but still never reach the retina display. So two comments. Have you seen the talk by Professor Sean Former and his students of the edge display, haptic edge display, this morning presented? So putting tangible controllers on top of the screen, make a competition or occlusion is not the best approach, but the edge side of the screen has a lot of potential. Even one-dimensional, you can do a lot of stuff. And they did amazing implementation and demonstrated today. And I hope you can think about not the I/O coincidence, but separate the controller to the edge of the screen. That's one comment. Second comment, if you really invest your energy and the time for the making high-resolution stuff, then it's better not stuck only for the controller. Knob, slider, mechanical knob slider, definitely better, currently better. But once you go to the operand, data, so information landscape can be really physical, which makes more sense. So go beyond the remote controller, like a knob or slider, seems to be a good way to justify your engineering effort. Thank you.
No, thank you very much. Yeah, we hadn't actually read that that paper. Well, I didn't see the paper this morning, but thank you very much. We can look into that.
Yeah, Giovanni from the University of Copenhagen. As far as I understand, you have used one of your prototypes has this flipping interface that provides a slider,
that's right, yeah,
and a rotary pot. So I'm just wondering, what's the difference if I give someone like a slider and a rotary pot, and I test the users with the same experiment that you have done? Does that make really a difference? Isn't that just the difference that the interface flips, this new interface is out?
Yeah, we wanted to simulate the controllers sort of disappearing into the device. So the reason that they flip is so that we can make it look invisible, if you like. I mean, they move from different locations on the board. I mean, yes, I mean, in terms of these results, possibly you would get very similar results if it was just a flat surface. But yeah, each position can hold a dial or a slider or be flat. So we'd have to have several different ones if we didn't have them disappearing and changing.
Yeah, I understand that. But the thing is that, so the concept that you proposed at the beginning integrates the two, right? The visual feedback that you have from the mobile, and then this interface emerge from the surface of the mobile. So I don't understand how the prototype that you have built, it doesn't integrate that. There is not visual and tactile together. So this is, I mean, I'm not sure if that really makes a difference with the regular sliders and pots. You could have given a mixer to someone and probably have the same results.
Are you referring to the high-res prototype now? Yes, the one that's got physical controls, or are you referring to the ones with the rods? The high-res prototype was for us to determine whether or not it's valuable. Not. Am I listening to a question here?
If I understand what you say, I think the fundamental difference between having a mixing board and this high-res simulation was that the position of the controller was controlled by the machine, by the computer. So the user didn't know in advance where the controller would be. Okay. So he had to look at the stimulus during the experiment, so he was controlling the stuff, but he had to look at the stimulus to know where the controller would be. So we wanted to see if he had to look at it, or if we could avoid looking at the control to do the task. Okay. So with the mixing board, you know where the controls are, you can get used to it, because it's always the same location. And here it's not the same, so he has to acquire them again and again at random positions.
Yeah, okay. I would argue that they also can change location depending, but yeah, it's okay.